Thank you all for joining us here in the room. Welcome to everyone who is joining us online. I am really excited to be able to welcome Dr. Sparkle Malone here today to talk to us. She is an assistant professor at Yale in the School of the Environment and also associated with the Yale Center for Natural Carbon Capture. She joined the Yale faculty in 2020 after being in the same role at the Florida International University in Miami. I have been aware of Dr. Malone's work for quite a while now. She has broad expertise in remote sensing and resilient science and Everglades wetlands, which is always really exciting. She's been a leader on several networks. Both for her expertise in very specific biogeochemistry and methane ecosystem impacts and processes, and also for her depth of expertise in leadership and collaboration in those networks, both through the LTR and Ameriflex, and I had the pleasure of finally meeting her in person this past year through the NEON Advisory Council, for which she's currently the chair, and doing an amazing job running that show. And so I'm going to let Dr. Malone take this over and tell us about her work, and I hope folks here will join us for lunch afterwards and have more of an opportunity to talk with her. Folks online, please, if you're new to our seminar program, go ahead and use the chat to let us know where you're joining us from. If you have questions, there's a Q&A or chat tab that you can use. Put those questions and I will interject those into our question and answer following the talk. So with that, thank you for coming and take it off.
Thank you for the great introduction. And so thank you all for allowing me to come here and share my research with you. And I look forward to having a conversation about your thoughts about methane dynamics at the end. And so currently we've caused about 1 degree Celsius of warming. And with this, we're seeing significant changes in ecosystems, how they're functioning, our understanding of those ecosystems, and what we should expect to occur in the future. And methane is responsible for about 42% of this warming that has occurred since the Industrial Revolution. And so over the last few decades, we've been seeing steady increases in methane concentrations in the atmosphere. That kind of slowed down in the 2000s, but by about 2006, it began to pick up again. These patterns in the rate of methane concentration increases in the atmosphere are occurring, and we're not exactly sure why. We don't know if this is dominantly occurring because of anthropogenic impacts. Well, we know that it's occurring because of anthropogenic impacts, but we don't know if it's strong changes in just anthropogenic sources. We don't know if it's strong changes in natural sources or what kind of combination of the two is going on to lead to these changes in the rate of methane concentration increases in the atmosphere. But it is really important that we figure out what's going on, especially since methane is one of the most important mitigation strategies that will likely lead to changes in global warming in the near future. Natural emissions really remain one of the most uncertain point sources for methane dynamics. And so the answer that you might get in terms of whether or not there are substantial changes in wetlands, other natural areas, or anthropogenic sources is really dependent right now on the approach that you take. And so we have these top-down approaches that rely on atmospheric inverse modeling. They know the answer. They know what the concentration and how that concentration has changed in the atmosphere. And they're trying to figure out exactly where did it come from. And then you have these bottom up estimates that are from point source estimates of fluxes from particular locations, ecosystem types, or industries that we use to understand exactly how much methane do we think is being emitted, but it doesn't line up with the top-down sources and they know the answer. And so there's this weird overestimation that's likely occurring from bottom-up estimates, and the top-down approaches aren't necessarily particularly good at identifying what sources are responsible for these changes. And so we have these large mismatches in terms of our global budgeting that we have to really figure out before we really understand what's going on with methane, what kind of sources are changing, and what does that mean for future climate dynamics. We also know that half of global methane emissions are coming from very highly variable aquatic ecosystems, but the boundaries for these aquatic ecosystems are changing. The variability of methane fluxes within those systems is quite high. And so we still have a lot to figure out in terms of what's going on within these different ecosystem types to know exactly how that's going to influence atmospheric concentrations moving forward. We also know that methane fluxes, they not only vary by the type of aquatic system that you're looking at, it also varies by the type of vegetation that is dominating that system. And so if you're looking at particular wetland ecosystems that have forb or graminoid species dominating those systems, you tend to have much higher methane fluxes compared to ecosystems that are dominated by shrubs or wetland systems with trees in them. And so we know that the type of vascular plants that are within a system also influences the capacity for those systems to serve as sources of methane into the future. And this effect is largely because vegetation can supply liable carbon compounds. Vegetation can also support oxygen transport and increase oxic conditions, sort of pushing systems to oxidize some of that methane that is produced. But those same systems or vegetation can also help in the opposite direction, where it can mediate transport of methane directly from the soil, bypassing oxic layers and increase methane emissions. And so you have all of this variability that has to be accounted for when we're trying to figure out exactly what's going on with methane dynamics. It's influenced by the type of aquatic systems that are there, the amount or magnitude of that aquatic pool, the type of vegetation that's there, and all these things we have to try to figure out in order to really understand what's going on with the methane fluxes. And those fluxes are dynamic. They're responding to changes in conditions. Studies have shown that, of course, temperature of the air and of the soils has a pretty large impact on methane fluxes, in addition to the water table depth, which is variable, changing constantly over time with climate dynamics. And of course, the impacts of vegetation has also been noted across these different types of ecosystems. And most of this work has been focused largely on wetland ecosystems, because we know that the anoxic conditions that occur will really facilitate the production of methane. And so there's been a lot of attention to start understanding methane dynamics in the systems that are going to be sources. But there's been a lot less work done on focusing on the systems that will be sinks, because those sinks will typically be small, but they're vast in space, which could be partially responsible for the differences in our bottom up and our top down estimates. But what I'm really focused on right now is trying to understand what is going on with our natural methane emissions. How much methane is being emitted from these natural sources, and how is that changing over time? But in order to do this, I'm not going to be able to measure all of the locations where methane is emitted or being taken up into systems. And so I have to really figure out, with all of the infrastructure that we currently have, what are some of the best ways that we can scale up methane, and how can we do that in a way that's dynamic and that will allow us to detect changes in conditions and allow our estimates to have less assumptions built into them. And so to do this, I'm taking a bottom-up approach. I'm using eddy covariance towers that can measure the fluxes of carbon and energy, water between ecosystems and the atmosphere. And this can really help me understand, at least at the ecosystem scale, what's going on with fluxes. And for this talk, we're focusing mostly on methane. This type of data is collected across networks all over the world. In North America, we have Ameriflux, which works with principal investigators and other smaller networks to gather information, standardize it so that this flux data is available to the wider scientific community. It's how we have the MODIS-NET primary productivity product, which is also heavily based on flux tower data. This approach allows us to put towers in particular types of ecosystems that meet the conditions that are required for eddy covariance. We can put these towers that make high frequency flux measurements over ecosystems, and then understanding what's driving those fluxes within those ecosystems. If we have towers placed or distributed across landscapes, we can then use that information to make estimates for entire landscapes, for entire regions, and even the world if we have enough towers observing the types of ecosystems that we need. And so to scale methane, we're gonna really have to understand how the current placement of towers will allow us to do this. And these towers are mostly independent PIs will put up these towers in locations. And so this global network has not been designed to upscale methane or other fluxes to the global or even regional scale, because these are largely placed in locations where individual PIs will have their own science questions that they're trying to answer with them. And so now that we're at the point where we're attempting to make estimates at regional and global scales, we have to figure out how to use the data that's available appropriately in order to come up with the best models that we can with the information that's being captured at very odd locations all over the world. And so to really understand whether or not I can develop a methane budget for the United States, I decided to focus in on the towers within the US and figure out whether or not they are representative of the entire landscape or climate space that exists within the US. And so I know from previous studies that temperature and land cover are going to be really important. Understanding the moisture dynamics are going to be really important for understanding methane dynamics. And then trends have been detected with lat and longitude. And so working that into models will also be really important. And so if I think about how I should choose tower sites or information from this global network of eddy covariance towers, I'm going to figure out how representative the towers are currently for the United States. And so to measure the representativeness, I'm using all of this information about the climate and conditions that are occurring across the entire US. And I want to understand how much actual differences in climate space are occurring within the US. And I need to do this for current climate because conditions are changing. And so using long-term normals just won't work. And so I took all of the temperature, precipitation, vapor pressure deficit data from the US for the last few years. And then I want to measure how that variability changes in space and cluster up the US. And so I'm going to measure the dissimilarity of each location in the United States to every other location. And by doing this across the landscape, I can figure out exactly how representative the current eddy covariance infrastructure that's measuring methane is, and which would help me develop a sampling scheme that would let me make national budget for natural ecosystems. And so I first calculated the Gower dissimilarity, which takes all of this information about each location and puts it into a distance matrix, comparing each individual cell to every other cell within the US. After I do this, I can scale all of that information down into 2 dimensions with multi-dimensional scaling. And this will allow me to then cluster and divide the US into groups that's really driven by differences in climate and land cover type. And then I can measure dissimilarity within a cluster to see how well the infrastructure that exists within that cluster captures the dissimilarity that's experienced across the cluster. And with that, I can figure out what's the representativeness of the towers to that cluster to figure out if I can use the tower infrastructure that is within the US to create a national budget. And so when doing this, the US was divided up into 10 climate-driven clusters, and most of the variation between those clusters can be explained just by climate and location information. And once the US was divided into those clusters, I can measure the dissimilarity. And across most of the US, with dividing the country into 10 clusters, the dissimilarity is pretty low. But there are regions where this dissimilarity gets quite high. And you can see that in Florida, you can see that in the Northeast, in Southern Alaska, and in Hawaii, where those areas could have potentially been broken up into their own individual clusters. But to make sure that our infrastructure is representative of those areas, we would definitely have to have towers in those regions for models to work there. When I look at the representativeness across the tower infrastructure, for clusters that ranges anywhere from 0 to 88%. And so representativeness was actually pretty low for most clusters, but there were a few clusters, you can see EB and NEA, where representativeness is relatively high. And you know this because if you're looking at the dissimilarity for that cluster, which is the black bar, and the dissimilarity for the towers, if you have a lot of overlap, the bars should be about the same size, and that gives you the indication that you have towers distributed across the dissimilarity. And so it's likely that you can develop a model with the infrastructure that are in those regions, and they should represent those regions quite well. If we focus in on tower infrastructure that actually is designed to cover the US, like the National Ecological Observatory Network, their tower infrastructure doesn't actually measure methane fluxes, they are measuring methane concentrations. And so if I want to design a model that's utilizing methane fluxes, if NEON was measuring methane fluxes, our representativeness would be substantially higher in 6 out of the 10 clusters. But they're not doing that because that was the scope, but they should definitely do that in the future, because that would take us from having 2 clusters that we can make estimates for reliably to having 6 out of 10 clusters. And to fill the gaps in the other areas, of course, support for Ameriflux would help do that. But we don't just need the representativeness to be good for the clusters. We also need the representativeness to be good across land cover types. And when we look across land cover types, then we really realize where we're in trouble, because we're essentially covering no land cover type within a cluster adequately, except for maybe forest and NEA. And so when we use infrastructure that is just within the US, we can come up with pretty good estimates likely for forests in the Northeast, but that's pretty much it. But now we know our limitation. We would not be able to limit ourselves to just using infrastructure within the US in order to make those estimates of methane dynamics. We definitely have to look to the global tower infrastructure in order to do this. Luckily for us, the Global Carbon Project had created this product for FluxNet methane, where they went through all the towers that are reporting methane globally, standardized the data, and made it available in FluxNet Methane version 1.0, really enhancing our ability to make these global budgets. But because this product is available, we can use all of the tower infrastructure globally and see what kind of estimates we can come up with for methane dynamics for the US. And in order to come up with those estimates for methane dynamics, we're using site level information initially just to be able to figure out how well we can represent certain eddy covariance tower sites. We're using vegetation information because studies have shown that the flux rates vary by vegetation type. We're using climate information, which includes temperature, precipitation, and vapor pressure deficit. And we're using spectral information about the vegetation activity. We're using the enhanced vegetation index from MODIS and the normalized difference vegetation index also from MODIS. With this approach, we're creating 3 different types of models. First, our site level model, which will allow us to evaluate how well we can create a model for individual sites. Then we're creating a model that has removed the site level indicator so that that model would be projectable in space. And then we have a model that is also not using the vegetation class because at large scales, when we apply a very particular vegetation class, we know the reality is that that vegetation class is not homogeneous across that entire pixel. It's likely to be a combination. And so the third model is really helpful for understanding the uncertainty associated with not really knowing the distribution of land cover types that really exist within that pixel. And so the models that we can create to understand methane dynamics using machine learning aren't too shabby on first look. And so we can create a model at the site level and capture about 75% of the variance that's occurring across the climate and spectral variation that can occur. And this is creating models for monthly methane fluxes. When we remove the site level information, the amount of variability that we can explain definitely declines quite a bit, but our models are still usable on first look. And then when we're not even including vegetation type, we see even further declines in our ability to capture a lot of the variation that occurs between average monthly flux rates. We can see that temperature and vapor pressure deficit were really important predictors, and the vegetation class and spectral information associated with vegetation dynamics were surprisingly extremely important in predicting methane dynamics. Even though we know that they would be important, we didn't really understand that they would be just as important as the climate variables. And so we had to include the spectral information from the vegetation dynamics to really get the annual and seasonal patterns that we want to capture in a dynamic model for methane fluxes. But of course, when we dig deeper into how well these models work for individual vegetation classes, then we really learn that even on the global scale, we are not covering enough. We don't have enough representation in certain vegetation classes in order to represent them appropriately. And so we're doing pretty good on the wetland front and the grasslands, but we're not doing so well for mesic forests, for evergreen broadleaf forests. And so in order to really enhance our ability to make reliable and dynamic estimates of methane dynamics, we definitely need more infrastructure in certain land cover types in order to represent them adequately. When we look at how well these models perform, we can tell early on that we are going to have a few issues, that our models are definitely overestimating all land cover types except for wetlands and water, which are slightly underestimating with using this machine learning approach. We can take information, so using gridded climate data and MODIS layers for vegetation type, and then NDVI and EVI, we can take this information and project it into space to understand what is the expected methane emissions in 2020. And so we chose this year because you'll see later on that we can, in this year, other models, other biogeochemical model estimates are available. And so if we want to see how well this bottom-up approach will work, we want to compare it to some of the other bottom-up approaches that are currently being used. And so in order to do this, we're projecting in space our models with vegetation class and conditions in them. And to estimate uncertainty, we're using just the model for conditions. And then we combine it with a model that says, what if every land cover class within a particular cell existed? So kind of incorporating the uncertainty of unknowing, of not really knowing the distribution of land cover classes that exist within the cell. And what we see is that in 2020, our total estimated emissions for the US is about 6.03 techagrams of carbon. And when we look at the distribution of the methane that's being emitted from different land cover types, we can see that a large part of that is from grasslands because it covers so much area within the US. And then estimates are also quite high for wetland ecosystems and water bodies. When we start to dig into some of that uncertainty, here I'm showing you what would the estimates be if every location in the US belonged to a particular land cover type. So you can see here that if you're looking at G for wetlands, if the whole US was a wetland, we'd be looking at about 14.87 techagrams of carbon versus some areas, some of the forested areas where you tend to have much smaller methane emissions coming from them, and they're usually in the 5-6 range techagrams of carbon in 2020. If we look at our overall uncertainty estimate for 2020, we're looking at about 1.93 techagrams of carbon. To understand how these estimates compare to some of the other bottom-up approaches that are using biogeochemical models, I worked with Yumi Oh from NOAA, who ran the terrestrial ecosystem model. And this model is set up to simulate methane oxidation, methane emissions, and then come up with a total flux. And so the model takes both static and dynamic input variables. And some of their static input variables includes information like elevation, vegetation type, soil texture, soil total carbon, soil pH, wetland type, and grid inundation factor. And then the dynamic aspects of the model include information about leaf area, net primary productivity, air temperature, precipitation, vapor pressure deficit, and cloud cover. And then the model estimates both methane oxidation, methane emissions, and gives you a total flux. And so we compared the outputs from the terrestrial ecosystem model for 2020 to our estimates. And the terrestrial ecosystem model is estimating about 13 techagrams of carbon from the US in 2020. And some of the biggest differences between the estimates where we're using just the tower-based information to scale up, it has to do with those wetland areas which are being underestimated, and then our dryland areas for both models are really being overestimated. And that's largely because most of the measurements for flux dynamics are occurring in locations where people, of course, expect there to be methane. And because of it, it's really pushing all of these models to kind of overestimate how much methane is being emitted from these different land cover types. But to bridge some of the gap between our estimates for methane emissions from natural areas to the terrestrial ecosystem model, I decided to rerun this model instead of using land cover and climate information that I use from Terra and from MODIS. I'll use the land cover and climate information that is being used in the terrestrial ecosystem model to see how much of that difference is due to those differences. And so if I just look at how much change I get in my estimates due to land cover, I'm looking at about 1.68 tetragrams of carbon just by using the land cover that the terrestrial ecosystem model used. But if I use the climate information that they used, I then lose about 0.46 tetragrams of carbon, which would then put my estimate for 2020 at 7.5. And when considering the error that's in that estimate, there's still about 3 tetragrams of carbon that is unaccounted for. I'm not really worried about finding those 3 tetragrams at this particular moment, mostly because I know that the biogeochemical models are overestimating because we're all experiencing the same issue with limitations in infrastructure and having enough information from upland systems, which are likely to be a small but constant methane uptake, which would bring all of the numbers down. I also have to be concerned that even though I went to use all of the data that is available globally to make estimates for the US, that entire global data set doesn't actually cover the climate space that is experienced within the US. And so I still have about 13% of the US that is experiencing climate dynamics that is very different from the global climate infrastructure for methane. And so in order to really make realistic estimates for methane dynamics, we have to fill that gap in infrastructure, because otherwise we're going to continue to have this issue where we're extrapolating our estimates into areas where we have not actually observed those conditions. And then we're also going to have issues where we're making estimates for large parts of the United States where methane is likely to be taken up at really small rates, but we're not incorporating that in our models. And so we'll be overestimating natural methane emissions. And I believe that this is largely why we see these big differences between the bottom-up and the top-down estimates for methane dynamics, is because the top-down, they know the answer, and so they're going to get closer they're going to make their information line up with, of course, driven by assumptions, but they're going to distribute those methane emissions across all of these classes. But with the bottom-up approach, we are overestimating methane dynamics, and it's largely because so much information has been focused on measuring methane fluxes in wetland ecosystems and in aquatic systems where we know that we're going to have fluxes. We also know that these fluxes are super dynamic. And so in order to develop dynamic estimates with as few assumptions as possible, we're going to need to enhance our infrastructure in order to do that, because the biogeochemical models are going to make assumptions for how they think these processes are operating. But we know that a lot of those assumptions might be changing in the future as conditions continue to change. And so if we want to be able to make estimates from the flux data, we're going to have to increase infrastructure in order to do that. We are still measuring or capturing the same patterns that are seen at smaller tower sites or patterns that have been observed across wetland ecosystems where emissions are lowest in forested landscapes. And this is also compared to other wetlands, but if you just look at the vegetation type, you have lower emissions in forested and shrubland ecosystems, and then higher emissions in herbaceous ecosystems. And of course, improving our tower infrastructure within and across clusters would make pretty significant changes to our ability to estimate methane dynamics. And with that, I'll take any questions. I'm curious, so I know you're focused on the natural fluxes, and I'm wondering, when you compare that to maybe the more anthropogenic sources, do you think that it is, maybe this is unanswerable, do you think it will be harder to estimate the anthropogenic side, or is that actually a little bit easier because we have to track those more and maybe it's less variable, or how would you best compare the natural tracking to anthropogenic sources? Sure. And so if you're interested in understanding the ability to track natural versus anthropogenic, we have false confidence in our anthropogenic estimates because we're basing it off of what we know we used. And it's less based off of all of the waste fluxes that will occur, which we know now are huge. And so our false confidence in our anthropogenic fluxes would make us believe that they're accurate, which is why some studies go back and forth into saying, like, we don't know why methane concentrations in the atmosphere have been increasing at these crazy rates. I know why. It's because all this infrastructure is leaking out methane all over the place. And that would not show up in any budgets because no one is measuring the leaks. It's really hard to do that. There are new satellite missions that are being put in place to try to capture some of that. And we have Carbon Mapper. And so we are entering into the frontier where we're trying to actually understand how much waste there is and how much of the fluxes, how our budget needs to be adapted to incorporate some of that waste. And so even though we believe that our anthropogenic estimates are good, I'm going to say that they're not good. And it's largely because of all the waste. And measuring that waste is difficult. It's difficult because you're measuring it over surfaces that we usually don't do a very good job of being able to capture in remote sensing products. And so all of these coastal cities are really hard to capture. And that's usually an area where things are really gray with remote sensing, but remote sensing might be our best bet to come up with those anthropogenic numbers. And so I personally believe that the anthropogenic part is much harder to estimate, but it's not that the natural emissions are going to be any easier, because some of the limitations, some of the reasons why we don't have good numbers for methane uptake in upland systems is because it's hard to measure small fluxes. And the ability to do that and do it in space has been really difficult, but there are new missions and new satellite designs that are being thrown around. And so hopefully one day we'd be able to capture some of that in space with satellites, but it's difficult on both ends. It's really hard to get the natural ecosystems as well as the anthropogenic, but I'm blaming the anthropogenic definitely on the increase in methane concentrations in the atmosphere.
Thank you. Well, it seems like from the announcement you've done is a really telling case that we don't have enough bus towers in the right places. And on the other hand, those are not entirely cheap things to install, right? So I'm curious if you could talk about what is any hope for like inverse model to model to help kind of extract one thing from how we have and form where we need to put the new one, but it's really the problem just that
It's a combination. So we definitely need more towers, but the reality is that there is a ton of tower infrastructure all over the world. And so even the largest cost in putting in these towers is really putting in the physical tower, getting all this permitting done. But the reality is that we could utilize the existing infrastructure and do the cheap part, put the instruments on the towers that exist, and then provide support for individual PIs or networks to maintain those instruments. And so I don't think that it's actually a very big ask for us to take advantage of existing infrastructure and put methane on all of these towers that exist all over the world in order to come up with a better understanding of both methane fluxes, energy dynamics, and also CO2. We could do that for a reasonable amount of money. And so I think we have to just take better advantage of our infrastructure. And then when it comes to the inverse modeling, I think that it is actually really important for us to come at these estimates from different areas because they have different strengths. And what I appreciate about the atmospheric inverse modeling is that they have the answer and they are right. The answer, they know what the concentration is in the atmosphere, and they know how that has changed, and they try to back their way out of what could have happened with the potential sources. But that has to, a part of that is built-in assumptions. And so if some pattern with a particular source has changed, they'd have to alter that in the way that they're making assumptions in order to represent that well. But using bottom-up approaches where we're measuring these fluxes and we're trying to take out all these built-in assumptions, that would help us really understand how different source categories are changing over time. And so I think the atmospheric modelers are really good at understanding what's the effect and how the atmosphere is changing. And the bottom-up approaches are good at saying how the different categories have actually changed and maybe how those relationships between the drivers and the flux rates are changing as well. Yeah, so there's two basic ways that people are coming at these bottom-up approaches from. You either have people who are taking these flux measurements and looking at empirical relationships between the fluxes and conditions, and they're scaling it up. Or you have individuals who are taking that same type of flux information and then putting it into biogeochemical models to model the process and then come up with their estimate. And so both of us are plagued by the same problems. Where is that flux data available from? And that's why, in general, the two major bottom-up approaches are being still overestimating because we're still limited by the same problem. I think you, and then Peter, and then, okay. Yeah, I think that is definitely how we're going to have to move forward until we have sufficient infrastructure in different landscapes. The hardship, though, with that is that current networks are not collecting that information and not making it available. And so we're essentially like starting from the very beginning in the flux world saying, you know, we need to go back and get all of these other different types of flux measurements and figure out how to put them together so that we can utilize them. But it is possible because a lot of the biogeochemical models are taking flux estimates, not just from eddy covariance tower sites, but they're also doing like smaller chambers. And so the work is being done to figure out how to put all this information together. I personally like the towers because it removes the assumption that a lot of the fluxes are coming from the soil, right? And I would definitely want to get away from that, having measured fluxes moving through vegetation and moving through trees. I know that you can only get that at the ecosystem scale, and you're going to need a tower in order to get those estimates. And if I just relied on collars, then I would still be overestimating what my methane fluxes would be. But for the time being, we need to take advantage of all the data that's out there. Oh. Hi, Pete.
So this set it up. Can we put methane flux sensors on all the towers that we already have? I think it's a great idea, and I think the structure that you set up for saying, okay, I got if you like, I'm trying to put a new tower, bring up new towers involved, and they don't want to put a methane sensor on. But now I can say, well, if you put the methane sensor on, it's not a whole thing for incorporating the data into control a lot of things that help everybody just by putting that. But that was not my question. My question was, do you look at the data to look for anomalies or surprises? So some of the most interesting things from the tower data have been you got a bunch of wet sites that look like they ought to be producing lots of methane, but they're not because the surface is dried out 40 centimeters. It's all being consumed. So do you have and one way to sort out some of these mechanistic uncertainties, to look for surprises or anomalies. And are you doing that? Is it helpful?
Yeah, so Peter asks if we're looking for anomalies in the data, and definitely. And so what really got me excited about looking at methane dynamics is because I thought I knew where to expect to find methane, how I should expect to find it. But then actually going out into certain sites and looking at this data, I realized like all of this methane that's coming out of these coastal ecosystems, I'm shook. I had no idea that I would be getting such large methane fluxes from these coastal ecosystems that might even be forested, which also made my expectations go down. But all these ecosystems are emitting methane that I necessarily would not have assumed methane would have been emitted, which then is making everyone look for methane everywhere. And I swear, I feel like everybody's finding methane everywhere in these natural systems, right? And part of that is really understanding that you don't need to really be inundated to be producing methane. All this methane is being produced in soils that have sufficient moisture to create anoxic conditions. And if that's occurring within the rooting zone, you're going to have some methane being produced. And some of that methane is going to be moving through vegetation, which for some reason, I did not really realize in the beginning how much fluxes of methane would be moving through vegetation. And so to me, that was a bit shocking that there would be such a big difference between the fluxes that you're measuring with soil collars, which I feel like in my educational career, when I was thinking about methane dynamics, I'm looking at the soil, and that's where I thought I should have been looking. But it's very clear that no, this is happening at the ecosystem scale. This methane is moving through vegetation. And so really understanding the rules for how methane movement through vegetation is occurring across land cover classes will be really important for incorporating that into models into the future.
Interject an online question from Steve Hamilton. To extrapolate the relatively well-studied findings regarding natural emissions in the US and Europe to global emissions, what major land cover features that act as methane sources are not represented?
So I think that there are real limitations to the way that, oh, I'm sorry, I don't need to repeat that. Okay. There are real limitations to the way that we are treating aquatic ecosystems in the current land cover products that we have available to us. One issue is that studies have clearly shown that flux rates differ by the type of product, but with this approach where we have these land cover classes that are given very simplified categories, they're not designed to scale methane. And so we would have to make big changes in how much detail we're putting into aquatic and wetland ecosystems to capture that variability. And part of that works out across the US when I am surprisingly underestimating methane fluxes, but that's largely because for the tower sites where we do have information, I'm pulling down the flux rate by including forested wetlands with trees. And so I definitely need to separate that out in order to get adequate results in our models. And so it's not that the classes are missing, but how we represent them needs to be redesigned, thinking about methane and how methane varies across different types of systems, how it varies across aquatic systems. And we need to develop a land cover classification that's very specific to scaling up methane to capture that. There's definitely spatial heterogeneity. The issue with the image that I showed you was that I put them all on the same scale. And so by forcing everything onto the same scale, it makes it really hard to see the differences spatially, but they are definitely there.
I'm curious, with your data set, do you have a sense of whether or not emitting systems are increasing, and so that's like maybe the source that if you already have these systems that are maybe high methane, they're producing more, or are new systems seemingly popping up that maybe historically weren't mitigating.
Yeah, that's actually an analysis that we're working on running now to understand, because we need to have a more dynamic land cover product that would allow us to capture that. Right now, though, like if I assume that land cover was constant, I don't see changes from one year to the next. I don't see substantial changes from one year to the next. It looks pretty constant, but I know that that's completely limited by the land cover product not changing. Like if that is static, that is it has a huge effect on what your estimates are going to be. And so keeping that static is a problem. It's also a problem not having a dynamic source of inundation cover. And so even if I had a land cover product that was not great, if I had a nice layer of what's inundated versus not, and that was dynamic, that would help offset some of the issues with that. But yeah. Oh, go ahead. Oh, question.
Important background. The rates of methane emissions was much lower high, showed that early. And so I was just surprised at the end when your message was, I think, we need more towers, especially in upland ecosystems, even though some of the data said there are almost no towers that measure rates of emissions from those. Why are you getting my special?
Okay, so the question is, why is my message not that we need more towers in aquatic ecosystems? And we definitely need more towers everywhere, and that's true. But of the systems that are really gonna hold us back in creating realistic estimates, I think it's the upland. And that's mostly because a lot of my attention has been focused on like, why do we have this big difference between the bottom up and the top down? And it's the overestimation of upland areas. And then when you go and look at where infrastructure is distributed or where studies are funded to measure methane dynamics, of course, it's in all these areas that the emissions will be great. And so I think that will continue. People will continue to do work in areas where emissions will be high because that's easy to fund. But what's not easy to fund and to get attention are places where the methane uptake is really small and constant. And so that's why I have been focused a lot on drawing attention to that, because even when we've made attempts to put infrastructure in locations where our flux rates will not be flashy, that is the response that we're going to get from reviewers. Why would you measure methane there? Because it would be really tiny, and maybe efforts should be focused on measuring large sources of methane, is the response that we'd likely get, without people really understanding the value of measuring small, steady methane uptake from systems. And without doing that, we can't actually make good budgets. But your systems are important too.
Given that they're mobile, they're often not.
So the question is whether or not there should be more of a focus on mobile animal emissions. And the emissions from animals, although there are studies that occur at the ecosystem scale where they'll like track animals and try to get figure out what the impact of those animals are on ecosystem fluxes. When they're really trying to understand what's the flux from those animals, I see most of that coming as like chamber studies, where they're trying to figure out what those estimates are by either attaching something to the stomachs of the cows or putting them in those chambers that are measuring their fluxes. The fluxes from mobile animals is shockingly huge, especially for the agricultural sector, which is a pretty big part of our methane budgets. And so it's definitely something that we have to focus on, because there's a lot of ways that we're going to have to come at to develop adequate strategies for methane mitigation. And so really focusing on understanding what kind of changes can we make to agricultural industries. And part of that will be making changes to mobile animals and how much methane they're producing. And there's a lot of research going into whether or not you can put feed additives and what kind of effect that they have. And those have like shockingly high success rates. And so people might be able to continue to eat burgers into the future. But a lot of work has to go into measuring fluxes in the agricultural industry as well as urban dynamics in order to come up with sufficient mitigation strategies. But I think it's really important to really understand like how much work is going to be done by these natural systems when we do our overall budgets. And it'll be really important to understand whether or not natural systems, the amount of methane that they're producing is changing over time, because that's one thing that we're not necessarily confident about. And we have reason to believe that it might change. And to make sufficient budgets, we'd have to have the infrastructure in place to do that.
Can I interject a question? A little tongue in cheek, but I'm curious about the movement in mixing capacity or rates and the landscape matrix. And so if you have 100 cows that are near an upland forest, do you actually get less methane emissions because the forest can actively take up the nearby cow emissions? Or is that process happening at a bigger scale?
Oh, we definitely need a tall tower to get at that. I would say that like some of this methane that's being produced from sources, I don't think that that's actually being overestimated. They're measuring that methane source accurately. But some of that methane, not all of it makes it up into the atmosphere, right? Some of it is going to be taken up by oxidative processes closer to the surface. And so it is possible that that is what is going on, or that, I mean, in the future, we could maybe develop dynamic landscapes where we put things in certain proximities, hoping to facilitate those processes. But right now, haven't seen any studies that can tell you how much being in proximity to a system that can take up methane might reduce your emissions, but that would be really cool.
It was really interesting that so when you think about farming, are there impacts with methane related to those climate changes?
So the question is, are there drivers of methane related climate change that might keep me up at night? Oh my gosh, let's go through the list of things that keep me up. So I am really, initially when I got into thinking about methane dynamics, it was partially because I had some panic about people are finding methane everywhere. Like this is a problem. And maybe this is why atmospheric concentrations are going crazy, because methane is just coming out of everything. It's just leaking out. And all of these systems, this is that positive climate forcing I've been hearing about, and it's happening. The methane is just going to leak out of all these systems, and then we're going to get super hot. Even though I like it warm, it's going to be a problem. And so it was that fear that really got me into looking at methane dynamics in natural systems, because I wanted to know, is the world turning on us? Like, has this gone too far? But then once I started really looking at the diversity of places that methane is coming out of, thinking about if methane flux rates were getting substantially higher from natural systems, then we should be able to see that. We should be able to look at flux rates that were measured a decade ago, and it should be very different than now. But that is not necessarily happening. I have turned most of my side eye to the oil and gas industry and infrastructure that's aging, that's leaking out methane unnecessarily, that is not related to how much methane we're using productively. And so I think that that keeps me up at night. And I recently moved to the Northeast where you guys have a lot of gas stoves, and now I have a gas stove, and that keeps me up at night too. I'm like, do I smell? Do I smell gas? Is my methane leaking? Am I a problem now? And so it's all of these leaks in urban areas that's freaking me out right now. And it seems like they're everywhere.
On that note, we're gonna thank Dr. Malone one more time and adjourn the seminar.